So we'll begin with the chapter waves now. As you would all know, waves is a slightly new concept to people, reaching this in about 11th grade or sometimes in, early 12th grade or late 10th grade. So we all are at this point of time slightly unfamiliar with the concept of waves because all of our lives we had probably studied more of mechanics and that side of physics. So this comes as slightly new to us and it looks slightly strange, but it's not. It's only classical physics. So there's nothing very strange about it, and you will see that it's a beautiful concept and it helps us do so much more with physics and our understanding of how things work in the universe. Waves is a very significant topic in the sense that it is the beginning of many new areas of physics that you will come to know now on about. So what exactly are waves?
Yeah. Waves, these transfer energy from one point in the medium to another point in the medium. But they don't transfer the mass to transfer this energy. That is the advantage with these waves.
Right.
So, for example, take mobile phones.
Right.
You talk with your friend on your mobile phone.
Right.
So, how is the information transferred?
Right.
It is transferred in the form of waves. And take another very common example.
Okay.
Take a tub of water.
Right.
And then drop a stone from top.
Right.
What happens? Ripples are created, concentric ripples.
Right.
And they move outwards.
Okay.
This is an example of wave.
Right.
And then take a rope, tie one end of the rope to a wall.
Okay.
And then try to move the other end, the other free end with your hand. What happens? Waves are created on the rope.
Right.
So what is so special about these waves? All these waves need a medium to propagate.
Correct.
And this medium has few elastic properties to restore the particle to its mean position.
Right.
So this creates wave in the medium.
Okay. So we need elasticity so that particles can come back to their mean position.
Yeah.
Okay. So
and
that is the requirement.
And due to their oscillations, the energy is transferred from one particle to another.
Right. So we see what mechanical waves are, and there are usually two kinds of waves, and not just mechanical waves. Actually, all waves can be usually categorized into either transfer waves or
longitudinal waves. And in this, since you are beginners, we are mainly going to focus on mechanical waves.
Right.
And there are other types of waves also, but this is bit out of scope of the course.
Right.
So let's go and see what transverse and longitudinal waves are.
Okay.
Transverse waves, the displacement of the particle is perpendicular to the direction of propagation.
Right, like that example you just showed.
Yeah, what does this mean exactly? I have shown this rope example. What is happening here? The particle, I'll try to draw this little big.
Right.
So this is the rope.
Okay.
And suppose this is after oscillation, this is the rope in this way.
Right.
So what happens? The particle at this point has moved up.
Okay.
After some time, this wave becomes in this way.
Right.
So the wave is propagating onto right.
Right.
And the particle is moving this way.
Correct.
So both these are perpendicular to each other.
Right. Hence the word transverse.
Yeah.
Okay.
So these type of waves are called transverse waves.
Correct. And then there are longitudinal waves.
Yeah. What are these longitudinal waves? The best example for this is the pressure waves created because of your voice.
Right, exactly. Sound.
Yeah. So I speak here.
Right.
What happens? I create a pressure difference at this point.
Okay.
Now this pressure difference is carried on to the next points.
Right.
So this is how it happens. First a compression.
Right.
Then a rarefaction.
Right.
Then a compression.
Okay.
So this is what happens. And since there is a compression here,
right,
these particles try to move into this area.
Okay.
And
so on that chain continues.
Yeah. And so on this chain continues.
Okay.
Here the oscillation of particles is in this direction.
Right. Along the direction of propagation.
And the wave is also propagating in this direction.
Correct.
So these are called longitudinal waves.
Okay. So we just saw what transverse and longitudinal waves are. So now we go to what a pulse is.
Yeah. Let's see what a pulse is. I'll again take the rope example.
Okay.
So at the free end, I'll just give one jerk, just a jerk. I'll move up and again come here.
Right.
So what happens? Something like this is created and
it
this
travels
goes
along the rope.
travels along the rope.
Right. So this is how you like that familiar action of of the typical hunter which people use with like animals, and it's very cruel, but but that's what they do. Like one whip and that thing travels along the rope. Correct.
Yeah, that is a pulse.
Right.
So a wave is a periodic sequence of pulses.
Right.
So I create these kind of pulses again and again. What happens? Once I move up and come down, come to the mean position, again I go down and come to the mean position.
Right.
So these kind of pulses are created.
Okay.
And the wave is formed.
Right. So basically the same action which you use to produce a pulse, if you keep repeating it, then you'll get a wave.
We get a wave.
And this is a very nice way to explain how a wave is actually a periodic sequence of pulses.
Yeah.
Right. Okay. So that was what a pulse is. And we now come to what a traveling or a progressive wave is.
Yeah. Let's see what a traveling wave is. Let's take a very, very large lake.
Okay.
I throw a stone at the center.
Right.
What happens? The wave goes on propagating. Something like this is called a progressive wave.
Right.
Which goes on propagating from one point in the medium to another.
Okay.
It's also called as traveling wave because it goes on traveling.
Right. We assumed a very large lake because we didn't want things to get reflected back and disturb the wave. Right.
And then, we have seen conceptually what waves are, but how do we represent them mathematically?
Okay. So this is where we translate from qualitative
to a quantitative
Exactly.
topic. Yeah. So this is the most general form of a wave equation. Y is equal to f of omega t plus or minus kx.
Right. So it has to be a function of both time and position.
As well as position.
Right.
Yeah.
Because you can see that different particles at different positions move at different points. Okay. And there obviously it's a function of time. Right.
So this is the most general form of the wave. And there are many examples. It can be in the form of e power minus x minus t.
Right. So any linear combination of t and x actually you can represent it.
And this function has some constraints that we are going to see next.
Okay.
So what is omega? It is 2 pi nu, and nu is the frequency of the wave.
Right.
And nu is 1 by t, where t is the time period, and the time period definition is same as what we saw in the SHM chapter.
Correct.
And then we encounter a new parameter called k.
Right.
K is called as wave number.
Okay.
It is equal to 2 pi by lambda.
Right. So it is related to lambda in the same way as omega is related to, let's say, frequency.
Yeah.
Okay.
Omega is related to time period because...
Time period. Okay. Yeah. Right.
And then, how do we identify in which direction the wave is traveling? Till now we have seen 1D waves.
Okay.
So how do we identify the direction of the wave?
Right. So in 1D that means either going right or going left.
Yeah.
Okay.
So how do we identify that? Suppose I have f of minus omega t minus kx.
Correct.
This means that the wave is moving in positive x direction.
Okay. Because the sign of the coefficients of t and of x are same. Oh, is it the other way around though?
Yeah. When it has opposite signs, it is moving in positive x direction.
Okay.
When it has same signs, this is positive x.
Okay. Right.
Now suppose it has both minus.
Right. Okay.
This means negative x.
Right. So actually to check how this happens, you can actually put, let's say,
plug in the values of x and t and then go on see
exactly.
how the
You
wave
can,
is
for example,
propagating.
start by putting one of them equals to 0, and then you can check what is happening. For example, if you put t equal to 0, then we have the position of all the particles at t equal to 0.
Yeah.
So you can see what goes on there, and then let's say you assume t equal to 5, and you still have x equal to 0. So you, based on what you know about the wave, you can easily find out what direction it is traveling. A shortcut here is to just remember that the normal formula, the standard formula which most people encounter every time is omega t minus k.
Minus k.
So that is the way most people remember it is, since this is the familiar formula, and the familiar way for a wave to travel is to from left to right.
Yeah.
So omega t minus kx represents a wave from left to right.
Left to right.
Correct.
That is in positive x.
Okay, so which means along the positive x direction, and the opposite thing is from right to left, the negative x direction. Correct. So that is how you can understand it, so that you can remember it better. So,
and then all functions can't satisfy a wave equation.
Right.
A wave equation should satisfy this particular differential equation.
Okay.
And this differential equation says dou square y by dou x square is equal to 1 by v square into dou square y by dou t square.
Right.
Where v is the velocity of the wave.
Okay. So you, as to how exactly this equation is intuitively related to the progression or of the existence of a wave, that you will understand later in life when you are more familiar with what partial derivatives mean.
Yeah.
But for now, we would like you to know that any function, any wave which is and actually for a function to be a wave, it should satisfy this condition.
Yeah. And then wave can't. As x goes to infinity or t goes to infinity, the wave function can't go to infinity.
Right.
It has to tend to 0.
Okay.
Suppose I take e power x.
Right.
Or e power x plus t. When x and t both increase, the function increases.
Right.
So these kind of functions can't be wave equations.
Exactly. And this result is in fact a different form, and in fact it is derived in a way from the conservation of energy, because if it went to infinity, we would have infinite energy associated with the wave, which we never have, obviously. Okay.
And then what is harmonic wave? Like this is the wave equation which we are going to deal for most of the times, because it is very easy to manipulate and get the physical significance.
Right.
And it is periodic in nature. The first important property is it is periodic in nature.
Correct.
It repeats itself.
Yep.
And it can be written in two forms. One in the sinusoidal form and the other in the cosine form.
Obviously, both of them are interchangeable,
Yeah.
which you can, you know enough trigonometry to change from one form to the other.
Yeah.
Okay.
And you see a parameter phi here.
Right.
This is called the phase constant, which is same as what you saw in SHM.
Right.
This value depends on the initial values, that is the initial displacement at time 0.
Right. So
And the velocity at time 0.
Right. So given initial conditions, we can always determine the initial phase,
the
and
value
the
of
phase, since it's constant, we have it for the rest of our work.
Yeah.
Okay.
And then coming to the velocity of the wave.
Right.
Velocity of the wave is equal to nu into lambda.
Okay.
Where nu is the frequency and lambda is the wavelength.
Right.
This is a very basic formula which you have encountered somewhere in 10th standard, and we'll be going to use this very often.
Okay. So now we'll see what how reflection and transmission of waves works.
Yeah. So, for example, take a rope. Take two ropes.
Okay.
With two different thickness.
Mass densities.
Yeah, thickness,
Okay.
mass densities, anything.
Right.
Which is connected to the wall.
Okay.
So, if I give a pulse at this end,
Right.
or let's say wave,
Okay.
which is more familiar.
Hmm.
If we give a wave at this end,
Right.
the complete wave doesn't pass to the next rope.
Okay.
Some part goes into the next rope,
Hmm.
some part comes back.
Right.
So the part which goes into the next rope is called as transmitted wave,
Hmm.
and the part which comes back into the rope is called as reflected wave.
Correct.
And the most important thing which you have to note is when the wave goes from one medium to another, the frequency doesn't change.
Right.
Like this is the key to solve many problems.
Because you need, in many problems, you'll not know where to start, and this
Yeah.
is often where to start. Okay.
Exactly.
So we saw what basic waves were and what different kinds of waves were, and we came to know slightly more about waves. We saw about characteristic equations that differ, that make certain that whether a function of time and of position is really a wave or not. We saw the condition for finite energy that results in the fact that a wave at infinity cannot have infinite amplitude. And then we saw what the expression for velocity of a wave was, and we saw what reflection and transmission of waves is. And it's a very interesting concept that waves can also reflect and transmit at the same time. This is not something we are familiar with when we are dealing with solid objects or particles. So this was some theory about waves, and we'll look at some more now.
Yeah. So with what amplitude does a wave reflect and transmit?
Okay.
These equations give you with which amplitude it reflects and transmits. AI is the amplitude of the incident wave.
Right.
Suppose I take the same two ropes example. I give a wave here.
Right.
The wave which I give is the incident wave with amplitude AI.
Right.
That is the AI, and then AR is related to AI with the velocities.
Correct.
since these are ropes, the wave can travel only if there is tension. So these tensions will generate some velocity in these waves.
Right.
So by calculating the velocities, you can get the amplitude of the
Right.
reflected and
And these are the
transmitted
expressions
waves.
for those, and you will find many materials in which you will see how it is worked out, how we arrive at these expressions. Okay. So as you can see, it's actually the forms are not very difficult to keep in mind, and it's always advisable in physics in such problems to have a clue about, because there might be questions which will be designed keeping this formula in mind. So it's better if practice about it and be familiar with it. Okay. So now moving on.
And then let's take few examples.
Okay.
Let's consider a wall,
Right.
and let's say that this is a rigid boundary. How does a rigid boundary behave? I have a rope here, I give a pulse. For
Okay.
example, I give
in fact,
a pulse.
this is a very important concept,
Yeah.
right?
I give a pulse here. So it goes to the end, hits the wall, and then comes back in this way.
Okay.
So there is no transmission, perfect reflection,
Right.
which is called as rigid boundary.
Okay.
And the important thing to note is the phase reversal is pi.
Right.
That means it has inverted by pi radians. That is how rigid boundary behaves.
And in fact, often in questions you will be asked to find the phase difference of the reflected
Yeah.
wave, and these are the boundaries are where it matters, and a lot of people get confused, and the correct answer and the wrong answer will be different by just pi or 2 pi, and this is where this concept is very important. Okay.
Yeah.
So there's
And-
another open end.
Yeah.
Okay.
There is this open end also. So
Right.
what is this open end? For example, take a pole and there's a ring which can smoothly move on the pole without any friction.
Right.
I give a pulse again. So what happens now? It goes to this end, but again comes back this way only
Okay.
with no phase change.
Right.
So this is how this open end behaves. And yes,
Okay.
these are the two most used boundaries in most of the questions.
Right.
So coming to the velocity and slope in a wave. So what are these? Let's take a wave.
Right.
So velocity, there are two velocities actually.
Correct.
One is the velocity of the wave, which we denoted by v,
Right.
and the other is the velocity of the particle, which we denoted by vp.
Right. And for most waves which we'll be dealing with, they'll be transversal. So both of them will almost always be perpendicular to each other.
Yeah.
Correct.
So how do we calculate vp?
Right.
The particle is oscillating this way, which is y-axis.
Right.
So dou y by dou t gives you vp,
Okay.
and that is what we did here.
Right.
And then these by few other manipulations, we get vp as minus v dou y by dou x.
Right. And I'll just like to drop a hint that if you proceed along these lines in a general form, not just a transversal, that is how you arrive at the wave equation which we saw in a while back.
Yes.
Okay.
And then what is dou y by dou x? It is rate of change of y with respect to x.
Correct.
So that means the slope.
Right.
So velocity of particle is related to the velocity of the wave with the slope of the particle.
Correct.
And then Vp max, as you can see, the value of cos omega can reach up to 1. So Vp max is a omega.
Right. Okay. So
So let's move on to velocity of wave.
Okay. So this was particle velocity, and now
Yeah.
we'll move on to velocity of wave.
So let's move on to velocity of wave in 3 different media.
Okay.
Say the rope which we have been seeing for a long time. So what is the velocity of wave in this?
Okay.
A wave can only travel in this rope if there is tension and if there is mass.
Right.
Because tension generates potential energy and mass generates kinetic energy.
Okay.
So these two are the important factors
Right.
for the velocity.
Okay.
And using dimensional analysis, you can easily get that V as under root T by mu.
Okay.
And in fluids, the shear modulus the
Bulk modulus.
bulk modulus B,
Right.
which is the bulk modulus, is the most important parameter, and rho, the density, is again important parameter for potential and kinetic energies
Correct.
again. So these two, again by dimensional analysis, you can get velocity as under root b by rho.
Right, and in solids it's like v equals to root of y by rho,
Yeah.
where y is the Young's modulus. So you notice a pattern here. We always have one element which ensures elasticity and one element which ensures mass.
Yeah.
This is for mechanical waves. Okay, so this is how you can remember. So there is no way you can actually forget what the expression of velocity is, because they're all very familiar, and t, b, and y are just corresponding elastic parameters in those media, and obviously mu and rho are per unit masses. Per unit masses are what we consider when we look at elasticity and velocity.
Yeah.
Okay.
An important thing is mu is mass per unit length,
Right, exactly, as I said.
and then rho is the density.
Okay,
So this is mass per unit volume and this is mass per unit length.
right. So obviously the units, the dimensions of
Yeah.
b and is different from the dimensions of t, and similarly for b and y have the similar dimensions. Okay.
And then coming to the most important principle, which is called as principle of superposition. This
Correct.
is very widely used in the next concepts.
Right.
So what is this? It says is suppose we have two waves y1 and y2,
Right.
and these two are acting on a same rope, for example, say. So how is the final shape of the rope?
Okay.
It is the final shape y is just the algebraic sum of y1 plus y2.
Oh, okay.
This is what the principle
Now
of
this looks very
superposition says.
intuitive, but when you explore a new area in physics, and you don't just start adding things. You have to verify the validity of such statements, and hence principle of superposition, although it sounds very familiar in almost every branch of physics or chemistry we study, but it is very important for us to arrive at this conclusion so we can use it, because if we can't do algebra on something, we don't know what to do about it. So that is why principle of superposition is a very important concept, and it's very, very significant.
And this doesn't work only for, this does work for 2 and even for any number.
Right. Okay. So that is why you see the sigma there. So we'll move on to standing waves now, which is again a topic from which we get a lot of problems in entrance examinations. Okay.
So what is a standing wave? In a medium, if two progressive waves are traveling in opposite directions with the same frequencies,
Right.
and they are superimposed on each other, we get
Okay.
standing waves.
Correct.
For example, again, let's take the most familiar example, the rope example.
Right. In fact, you can remember this diagram from a while ago when we created something similar.
Yeah. So I generate a pulse at this end.
Right.
I generate a wave at this end, for say. So what happens? It goes on and
Right.
hits at this end.
Right.
So from this end, as I have already said,
It
there
reflects
will
with
be
a phase difference of pi.
Yeah.
Correct.
So it comes this way.
Right. Okay. And
So-
given some conditions, this will be very stable, and those
Yeah.
points where it intersects the rope.
These points intersect.
Right, so they'll be the same and they'll be uniform.
Yeah.
Within certain conditions. We'll look at what those conditions are later.
So these kind of situations, we get a stationary wave.
Right, or a standing wave.
These
as
are
you call
called as stationary waves because it is confined to a medium,
it. Correct.
and it can't transfer any energy out of this medium.
Right.
And suppose let's take y1 as a sine omega t minus kx,
Okay.
which is moving in positive x direction.
Right, and y2 will be in opposite
Obviously
direction.
moving in negative
So
x
applying
direction.
superposition, we get this expression.
Yeah.
Okay.
So this is the equation of the standing wave.
Right.
So you can see that amplitude is a function of position.
Right.
So this you can intuitively feel.
Okay.
Let's take a string.
Okay.
Imagine you took a string and you have attached it between two walls. Now if you pluck at the center, say
Right.
at the center, you get pattern something like this. So the amplitude at each and every point is function of x.
Correct.
The amplitude is maximum somewhere at the center,
Right.
but the amplitude at other points is less than that point.
Right.
So it is a function of x.
Okay, and here when we say amplitude, we mean the term outside the sinusoid. Okay, like in waves also, amplitude is a function of position, but here the term outside the sinusoid is also a function. In fact, that is the only function of position that we have. And so here the difference from a traveling wave is that at certain x, at a certain x, that particle will never attain more than a certain amplitude.
Exactly,
It
yeah.
won't go to the maximum amplitude.
That is
possible for
2a.
that wave.
only certain points can reach this maximum 2A.
Correct. Whereas in a wave, almost every point,
Exactly.
almost every point actually goes to the maximum amplitude at
Yeah.
some point of time. Right. So
Exactly.
this is how standing waves are different, and we also have that. We also have points of maximum amplitude, which we call antinodes, and minimum amplitude, which we call
Which
nodes.
are called nodes.
So if we're going from the formula, we can simply see that we can find out the distance between successive nodes and antinodes, and we can work that out, and that comes out to be lambda by 2. It is a very trivial exercise, and we leave it to you.